Hello class. This is a redo of Chapter 6, Early Primate Evolution. I've got a new cam, so this should be better. We're going to talk about fossilization, dating fossils, characteristics of mammals, traits and history of primates, hominoids, adipoids, anthropoids, hominoids, and evolutionary relationships among fossil primates. Let's get started. Why care about 30 million year old dead primates? Early primate fossils show adaptations that include stereoscopic color vision, grasping hands, greater dependence on hand-eye coordination, and adaptation to arboreal life and hunting insects probably drove that in natural selection. There's changes to brain-to-body ratio and the wiring of the brain in primates. The brain is larger in primates than in mammals or in reptiles. This is leading to a more complex social system. Social relationships are essential in primate societies. That's why we read about reconciliation. While there is aggression, reconciliation allows the group to live together. And again, primates' adaptation is about sociality, is about cooperation. Following early primate evolution, we can observe the stages and developments of change. We can watch the nervous system develop. We can see with apes today the kind of intelligence in being able to fashion tools, to modify branches, to make termite fishing wands or ant fishing tools. Fossilization. Here we have a 47 million year old primate fossil found in Germany's Messel pit. This is a primate. You can see it's early on. It looks like an abatoid, amomoid, or haplorhini. It has opposable thumbs, but it still has a very mammalian type body. This is a very common type fossil that we usually think of, bones that have been fossilized and remain in the dirt. In the center, we have the Laetoli footprints. This is also a fossil. What we have here is some volcanic ash in Africa that was fresh when these footprints were made. Because of the depth of the footprints, it's speculated that there was rain. And because it's volcanic ash, it can be dated chronologically by potassium-argon dating. On the right, we see the process of fossilization. You have a primate. He's walking around having a nice day, and then he dies. I'm not sure why, maybe a heart attack. But the dead body rots on the ground. It can be predated by predators. It can be stomped on by herd animals. It'll certainly be rained on, and the processes of planet Earth will drive it into the ground, where the moisture and rain that comes in will mineralize the fossil bone as it rots away. This does not happen with every bone that rots in the soil, so fossils are very rare. And then, as we see, someone comes along and begins to dig in the ground, and if they're digging in the right place, they can uncover a fossil. So that's a pretty random by chance act as well, even though there is research to look in areas where hominids would have lived. The amount of fossils in the ground is very minuscule compared to the amount of life on Earth. The amount of fossils we will find is even smaller. Dating fossils. Provenience is essential. It is the original, precise location and position of a fossil or an artifact. How deep is it from the surface? And what is its north by west orientation? That will give you an exact place in this site, as well as on planet Earth. The depth will tell you what time it's from. Dating fossils, there's two broad categories, relative and chronometric. Relative dating basically tells if something is older or younger compared to something else. It does not give you an exact time. Ways of doing this are stratigraphy, faunal correlation, and fluorine dating. Chronometric gives an approximate age in time. Radiocarbon dating, potassium to argon and argon-argon dating, dendrochronology, and thermoluminescence. Let's get started. But first, half-life. Half-life is the time period in which 1/2 of the amount of radioactive isotope, like say potassium, is converted into its chemical, its daughter product or gas, which would be in potassium's case argon. So, for example, potassium argon. After 1.25 billion years, the amount of potassium that was in the rock to begin with will be half. And we know the content to begin with, so we know how old that fossil is. After 2.5 billion years, 1/4 remains. And therefore you get a chronological time period. Now let's go back to relative dating. Stratigraphy, faunal correlations, and fluorine dating. Stratigraphy. This is the layers of the Earth. You can see from this photo, the very bottom layer is the rock base. We have soil on top of that with some scattered rock. Then we have another section of hard rock base. Another section of soil. Then the soil on top. The ground soil, rock, and plants, the grass. This is stratigraphy. The idea of relative dating by stratigraphy is based on the law of superposition, that a lower stratum, a lower layer in the Earth, is older than a higher stratum or a higher layer. And this is very much true. However, changes happen in the Earth, and we see this area of mixed strata over on the left. For that mixed strata to be there, it is younger than everything else, because everything else has to exist for that hole to be dug and then refilled. So in stratigraphy, when you're looking for something that is older or younger than something else, you have to bear in mind that the Earth does change. Faunal correlation. This is referred to as dating by association with index fossils. So are they the relatively same time as these index fossils or not? Index fossils, elephants, horses, pigs, rodents, some monkey species have been used as index fossils since they underwent relatively rapid evolutionary changes that are identifiable in their teeth and other skeletal parts. Their bones were frequently found in association. So what we can find is it older or younger than an index fossil, the fossil we found? Relative dating techniques, fluorine dating. As time passes, the organic components of bone, mostly fats and proteins, are lost, primarily through bacterial action. At the same time, percolating groundwater deposits trace amounts of fluorine into the bone. As a result, the amount of fluorine progresses increasingly. If the bones of two animals are buried at the same time in the same site, they should have about the same amount of nitrogen and fluorine. So they are about there at about the same time compared to each other. We don't know when that time is, though. Now let's move on to chronometric dating. There are five kinds we're going to talk about: carbon-14 dating, potassium-argon, and argon-argon, fission track, thermoluminescence, and dendrochronology. Let's get started. Carbon-14. In carbon-14 dating, neutrons in cosmic rays strike nitrogen-14 atoms in the atmosphere, releasing a proton and creating carbon-14. Carbon-14 and oxygen enter living organisms with every breath. The death of an organism stops the intake of carbon-14, no more breathing, and decay begins. Carbon-14 continues to disintegrate at a known rate. Its half-life is 5,730 years. So after it's been there, after that individual or that organism has been dead for 5,730 years, half of the carbon-14 will be left. The ultimate length of dating materials is up to approximately little less than 100,000 years, but the most accurate is less than 50,000 years. Potassium argon and argon argon dating. Here again we see a picture of the Laetoli footprints, and this was able to be dated because the footprints were made in fresh volcanic rock or fresh volcanic ash that had not turned to rock yet, and so it gives us a pretty accurate date of when these two, possibly three, Australopithecines were walking across this area. Potassium argon. Dating involves the decay of potassium into argon gas. And again, the half-life of that would be 1.25 billion years. So the initial amount of potassium will be half in 1.25 billion years, so we can judge how old that rock is. Fission track depends on the tendency of uranium-238 to undergo spontaneous fission. Boom! Energy released in the fission process ejects two nuclear fragments into the surrounding material, causing damage paths called fission tracks. These tracks can be made visible under a light microscope by etching with an acid solution, so they can then be counted. Generally, it is thought to be most useful in dating in the window of 30,000 years to 100,000 years. So a fission track could be used in combination with carbon-14 to verify dates. And this kind of cross-checking happens all the time. Thermoluminescence. Technique for dating certain archaeological materials, such as stone tools and pottery, that have been heated in the past. That release stored energy of radioactive decay. These things release stored energy of radioactive decay as light upon reheating. And here we see two statues, or clay urns. The left was created by the Zapotec about 1,500 years ago. The urn on the right was shown by thermoluminescence dating to be a forgery. And you can kind of see the preservation on the one on the right is much better anyway. But it's through thermoluminescence that, in fact, we're able to tell that. Dendrochronology. Tree ring dating is the method of scientific dating based on the analysis of tree ring growth patterns. By counting the thin bands, the rings within a trunk of a tree, the approximate age of the tree can be determined. Each ring is 1 year. 1 year of growth. The tree can be accessed via a bore, like shown in this picture. Multiple trees can be cross-checked, and the type of ring for that year can indicate weather patterns.